All right, so the stuff that we're going to talk about today builds on the stuff that we talked about before break about splines. We did quadratic splines last time. We talked briefly about linear splines. Linear splines literally were just plane connected dots with line segments, right? You have a bunch of dots, you find the line segment from dot 1 to dot 2, the line segment from dot 2 to dot 3, and so on down the line. Basically what you're doing is making a continuous piecewise linear function, but not paying any attention to the slopes. So when we did the quadratic splines last time, we said, okay, we're going to be a little bit more sophisticated. We're going to not only make the points match and make it continuous, but also make the slopes match so it is nice and smooth. That's what we did with the quadratic splines last time. Literally was last time, right? Right before break. Okay. So today we're going to move on to what actually is going to be your next major assignment topic, and that's cubic splines. So we're going to take it to the next. We're going to take it to the next level. Not only are we going to make the function be continuous across all the points that you're given, and not only make sure the slopes match, we're also going to make sure the curvatures match. Right? So you don't have any rapid change in curvature. So at each of the points where we switch definition for one function to the next, they will butt up to each other, their slopes will match, and their bend will match. So the second derivatives will be equal at that point too. Yeah. I'm going to do it. I'm going to set it up. The setup is similar to what's in your text, but I'm going to set up the equations slightly differently than what's in your text. I found it in another textbook. I think it's a little bit more. Personally, I think it's a little bit more straightforward. We're going to use both Excel and Geogebra to help us do these things. So we do a combination of the two. The nice thing is that you can copy and paste over from Excel into Geogebra to help us solve some equations. So that is one of the reasons why I want to do it that way. All right, anyway, so just for cubic splines, just to I'm not going to write out the real long-winded definitions, but I will write down what we mean by this. So if you've got a set of points, so you've got x1, x2, out to xn, with outputs y1, y2, out to yn. Remember again, we'll have functions that go, we'll have a function that's defined from x1, y1 to x2, y2. We switch when we get to x2 and go from x2, y2 to x3, y3, and so on down the line. So if I've got n points, we'll have n minus 1 functions that we're dealing with, right? Okay. All right, so again, we want to find cubic functions. We'll say S1, S2, out to Sn minus 1, such that we want to again make this, the cubic spline idea is that we want to make sure we've got continuity, slopes, and curvature all matching. Okay? So we want to make sure that when we do Si of xi plus 1, when I look at the right endpoint of the ith cubic function, I want to make sure it matches the left endpoint of the I plus first cubic function. And this will be for I equals 1, 2, up to n minus 1. N minus n minus 1. Yeah, okay. So I want to make sure I'm at the last one. N minus, well, I want the last one to match the last one matches it by default at the last endpoint anyway. So yeah, n minus 1. I want to make sure that the derivatives match. So when I do the derivative at the left endpoint, I get the same as the derivative. Do the derivative at the right endpoint for the ith one. I want to make sure I get the same as the derivative at the left endpoint of the next one. And then the same thing for the second derivative. Yeah, the last one's by default. Yes, exactly. Yeah. All right, so when we set these up, we're going to set them up in a specific form to make things easy to compute. Again, an arbitrary cubic function is going to be ax, or a plus bx plus cx squared plus dx cubed. But it's not easy to set it up necessarily that way, because I have to worry about all the shifting stuff with the x1, the x2, onto the xn, right? So it's a little bit easier to start with if we suppose that our functions are S1. We'll start at your first one. Well, that one's pretty easy because if I do the shift, if I stick the shift in there already, I can do this with the y1. That'll be your first one, right? And then make sure that we do a shift on the other coefficients. So if I do a b1 times x minus x1, a c1 times x minus x1 squared, and a d1 times x minus x1 cubed. Here's what I mean by shifting it. It makes it a little bit easier because notice when I put x1 in here, I get y1, right? So if I set up all of my rest of these in a similar fashion, I automatically know what the constant terms have to be, right? So I don't have to worry about solving for the constant terms. So that continuity condition helps us get that y1 piece, but we're getting it anyway because we're setting it up by default to be that way. So you'll have an S2 will be y2 plus b2 times x minus x1 plus c2 times x minus 1 squared plus d2 times x minus, oops, this is x minus x2, sorry, x minus x2 cubed. So again, we're shifting it so that when we plug in x2, we get y2. So again, I don't have to worry about the constant term matching up. So continuing, we get to Sn minus 1. We should have yn minus 1 plus b sub n minus 1, x minus x2 plus c2, not x minus x2, x minus xn minus 1, x minus xn minus 1 squared, and dn minus 1 x minus n x minus x sub n minus 1 cubed. All right, so our goal here is to figure out, of course, what the b's, what the c's, and what the d's are. Right? Because we've already rigged it so that we know what the A's had to be. They have to be the Y's, right? You agree? Okay. So we're going to do this, like I said, we're going to do it in a little bit different fashion than what the book does. We're actually going to figure out what the C's have to be first, and then from the C's, build back up to get the B's and the D's. Okay. So let's talk about how we do that. And there's lots and lots of fun notation in here, so let's make sure we don't goof anything up. All right, I don't want any tick marks today if I can help it. All right, so let's think about the fact that we want to make sure that the first derivatives match. Okay? Well, if I look at the first derivatives, I can differentiate, these are polynomials, so I can differentiate these easily, right? When I take the derivatives of each of these, the constants are going to go away. The second terms here, the x minus x whatever, x minus xi will go away, right? Here, the 2 will come down in front. We'll still have an x minus xi in each of those. here, and the 3 will come down in front. We'll have an x minus xi squared for each of those, right? We agree? Okay. So when we do the derivatives, if I do S1 prime, just to write them down, I would have y1, not y1, I would have b1, and then a 2c1 x minus x1, and a 3d1 x minus x1 squared. The next one would be S2. You would have a b2, a 2c2 x minus x1, and a 3d x minus x1, x minus x2, and a 3d2 x minus x2 squared. And then so on down the line. I'm going to try to do this with minimal subscripts to start with, and then just write down the general formula at the end. Because I'm not going to make you reproduce all of this stuff again. I want to show you where it comes from. Because it's the same process at each endpoint, right? So I just want to do it for 1 and 2, and then we'll just write down what the general formula will look like at the end. Okay? So if I just concentrate on these two, remember when I plug in, there's nothing to plug in for the left-hand side of this one. This is your first one, right? So I don't get an equation out of this one, right? But I can match the right endpoint when I plug it in for S1 prime, has to match the left endpoint when I'm plugging it in for S2 prime, right? So in particular, if I plug in x2 here and x2 here, they have to match, right? So that, notice when you plug in x2 here, you get zeros on these two terms. All right? Another product of this being written in a nice convenient form for us, when we plug in x2 into the second one, those go away, right? So the equation we get, hello, how are you?
I'm good. Coach Kick apologizes.
Yeah, tell Coach Kick I don't believe her.
I practiced at 2. It was 2:05. I didn't know what time it was.
All right. So again, we're going to plug x2 into each of these. This last one, we're going to b2, right? That's all that's going to be left, isn't it? So we'll have b1 plus 2c1 times x2 minus x1 plus 3d1 times x2 minus x1 squared. That has to equal b2. Right? And then, again, if I did this with an I and an I plus 1, you can imagine it all just being with i's and I plus 1s. You agree with that? Now notice that this has, again, I told you we were going to try to first figure out what the C's were, and then build off the C's to get the B's and the D's, right? Okay? Well, right now I still have B and D with the C in here, so I'm going to come back to this equation. But of course, before I get to the second derivative, I had to take a first derivative, which is why I went ahead and wrote down this equation here. So now if we do the second derivative, what goes away? Yeah, the B1, the B2s will go away, right? Okay. So if we do the second, well, I'm going to mark this with an asterisk because we're going to come back to that one. Okay. So if I do S1 double prime, the B1 will go away. We're just left with 2C1, right? And then plus a 6 D1 times X minus X1. And it's going to look similar for the next one. So far, so good? Bless you. Okay. All right. And now again, we want to make sure that the second derivatives match up at those endpoints as well. For splines, they call them the knots, because you're tying them together, so they call them knots. Literally, that's why they call them knots. Okay. So we want to make sure that the second derivatives agree at the knots. All right. So when I plug x2 into each of these, they ought to be equal. Again, when we plug in x2, this piece goes away, right? Agree with that? That piece goes away. So, in that case, what do we get? We have an equation that says, I'm going to put another star by this one. We'll have 2c1 plus 6d1 times x2 minus x1 equals 2c2. Right? Now notice, again, remember our goal, because I told you it was our goal is to try to figure out the C's and then back build and get the B's and the D's, right? But I haven't figured out the C's yet. We'll talk about how we figure out the C's here in a minute, okay? We haven't figured out the C's yet, but notice if I know the C's, I can figure out D1, right? At this point, I can solve this thing for D1, can't I? In terms of the C's. You get D1 is equal to what? Well, you would subtract the C1, 2C1 over and divide by the 6, x2 minus x1. So you would have C2 minus C1 over 3 times x2 minus x1. We agree? Okay. All right. So just to simplify the notation for us a little bit before I write the general formula, you can imagine that this is going to pop up every single time, right? Because if I do this for D2, this should be C3, C2, X3, X2, and so on down the line. But this difference should remind you of a delta X idea back from calculus. So we're going to use that notation. So for a notation purpose here, we're going to say delta sub I, little delta sub I, because we're also going to have a capital delta sub I here in a minute. Okay. Little delta sub I is going to be your x sub I plus 1 minus your x sub I. Okay. So if we extend this formula, your D1, or your D sub I mean, should be C sub I plus 1 minus C sub I over 3 delta sub I. All right, so that's one formula we need. Yeah.
Where again did you get the two slides? What did you do?
I plugged in x2 for x into both of them, the two equations above. I plug in x2 in for both of these.
Okay.
This term goes away, and I set them equal to each other.
Okay, makes sense.
Okay.
Thank you.
Yep. All right. Good with that? All right. So again, if I know the C's, I told you our goal here is to try to figure out the C's and then figure out the rest, right? If we know the C's, then I know the D's. Right? You agree? Okay? So now we can use that to get the B's using the start equation at the top of the screen. Because now I can plug in what D is, right? I'll use the formula with the 1 here as opposed to the I's, but I can plug this up here and figure out what the B's have to be, right? I've got 2 different B's in there. Where do I want to plug that in? Lost. Oh, I know where I want to plug it in. I don't want to plug it in. I need to come back to this one later. I need to plug it in back up to the... I need to plug it back in up here to this one. I have 2 B's in that one that I starred. I need to go back all the way up to the top one. I know, if I know Y1 and I know C's, I know the D's, so I can figure out the D. I need to go back up to the top one is where I need to go. So, all right, so remember that I'm going to do it with the 1s, and then I'll go back to the I's. Our S1 of X is y1 plus b1 times x minus x1, c1 times x minus x1 squared, and then d1 times x minus x1 cubed. Right? All right, so I know that, I know what the other part is. Then we have our S2 of x is y2 plus b2 times x minus x2, c2 times x minus x2 squared, and d2 times x minus x2 cubed. Now again, these two have to match, right? These two have to match if I plug in x2. When we plug in x2 here, the last three terms go away. Right? So notice the b2 goes away. I get an equation that involves y1 and y2, which are given. We know those. If I solve for the d's or the c's, I know what the d is. I can figure out the b. It's the only one I wouldn't know at that point, right? Okay. So if we plug in the x2, we get the equation y2 equals y1 plus b1 times x2 minus x1, c1 times x2 minus x1 squared, d1 times x2 minus x1 cubed. Notice that the x2 minus the x1 is that delta 1, right? So I'm just going to put that in there. I'm going to put that in there as b1 delta 1, c1 delta 1 squared, d1 delta 1 cubed. I would subtract the y2, I would subtract the y1 over at this point, and I'd have a y2 minus y1. That was like a change in y. Much like we had a change in x, I used a little delta. I'm going to use a capital delta for that one. So this will be delta 1. So just again for notation, delta sub I will be y sub I plus 1 minus y sub I. So your deltas are representing changes. Little delta is for the x, big delta is for the y. So far, so good? All right. We would know what D1 is. What did we come up with for D1? That was C2 minus C1 over 3 delta 1. All right. And now we can solve this for B1. Notice that if I solve this for B1, I would need to take this capital delta 1 and divide it by the little delta 1. So our B1 would be capital delta 1 over little delta 1. And then I need to worry about these two terms. Notice that I can cancel little delta 1 with little delta 1 cubed, leaving a little delta 1 squared. Right? I've got a little delta 1 that I would divide through to solve for B. Right? So it's going to leave a single delta. Do you agree with that? Okay. So when we do that, what are we left with? Well, let's see. I've got a little delta 1 on top. Now let's see about the C's. Let's see, if I multiply this by 3 over 3, you get a common denominator here. I would have 3 minus 1 gives me 2 of them, right? and then I've got a single one there. So I would have a 2C1 and a, let me put a minus sign here instead. I would have a 2C1 and a C2, right? And it's a minus because I'll have to move it to the other side. So I'd have a delta 1 over 3 times 2C1 plus C2. Again, it's a single delta 1 because I've got delta 1 squared in both terms, so we're going to divide by it. I got a common denominator of 3, so I can factor that out. And then I had 3 C1s minus a single C1, so I had a 2 C1 in that case, so I combine the like term. And again, it's a minus in front because I would have to move that term to the other side. This all for me. Okay. So again, now we can write this in general. If we extend this, I can change all of these to i's, all the ones to i's. This would be an I plus 1. Right? So if we extend this, our b sub I will be capital delta I over little delta I minus delta I over 3, oops, 2c sub I plus c sub I plus 1. Wonderful, great. A lot of work to get to that point. We're not done. Okay. We okay with the derivations though? In particular, make sure you've got them boxed in your notes so you can come back and go. I'm not gonna be giving you an in-class quiz and stuff like that. It's gonna be a major assignment outside of class to do this. Okay. So you're not gonna have to reproduce this stuff, but you will need to use the formula, so make sure you have access to where they are. Okay? Fair enough. I don't want to have to try to make you well, I'm certainly not going to make you memorize these things because they're complicated enough, and here in a minute we're going to have to solve the system of equations. So it's all it's all the same process all the time. It's just the formulas are a bit complicated. I'm not going to make you memorize it, and then if I just give it to you on the quiz, then what was the point? I might as well just have you do it outside of class. That's my thought on the pedagogical process. And if you don't agree with it, no. If you don't agree with it, get a PhD and teach your own class. Not to put too fine a point on it, but anyway. I figure you probably want something outside of class more than inside of class anyway. All right. Finally now, how are we going to figure out these C's, right? Okay, so we used the second derivative to get our D function, right? Our D relation with the C's. We used the original function to get our relation with the B's. But I haven't figured out how to find out the C's yet. Well, to find out the C's, I need to go back to that derivative relation that I started at the beginning and use it, okay? So that derivative relation that we had, if I go back up here again, that was our single star, it was that one here, right? This is our derivative relation. I now know what the B's are, so theoretically, if I knew the C's, I would know the B's, but I know, in particular, I know the B's in terms of the C's, right? I also know the D's in terms of the C's. They agree? Okay. So let's plug these things in and see if we can come up with an equation that would have to be solved. So, chances I remember that when I get down here. We had B1 plus 2C1 times x2 minus x1 plus 3D1 times x2 minus x1 squared equal B2, right? I think I remember that correctly. You're thinking, darn it, it could have been a check mark. All right, but now we have formulas for the B1, the B2, and the D1, right? We agree with that? Okay. So when we do this, we've got the B1 is our capital delta 1 over little delta 1 minus little delta 1 over 3 times 2C1 plus C2. That's B1, right? Again, I'm using a specific number here to start with, and then we'll just extend it later. Okay? All right. The next one, I don't have to replace anything. The last one, what was D again? That was, yep. Delta 1, yep, good. And then it would be times x2 minus x1 squared. I'm running out of room. Let's shrink it a little bit. Now B1 had a delta 1, a capital delta 1, a little delta 1, a C1, and a C2. So what's B2 going to have? Yeah, good. It'd be a capital delta 2 over little delta 2 minus little delta 2 over 3, 2C2 plus C3, right? So far, so good? Everybody's happy. Good. Good to see happy. All right. So we need to solve this. If we're going to solve this equation, I'm going to do it from a linear algebra perspective. I'm going to set up a system of equations, and then I'm going to do row reduction. So let's think about what you would do in that case. I would need to make sure that my constant gets over on one side, and my variables are on the other, right? Okay. This delta 2, capital delta 2 over little delta 2 is a constant. Capital delta 1 over little delta 1 is a constant, right? So I can move that over to the right. Okay. Okay. So put that on the right-hand side. Oops. So I've got that on the right-hand side. Everything else needs to go to the left. To make things a little bit nicer, at least from a relative perspective, in particular, I'm going to need to collect like terms with the C's. I really don't want to deal with the fractions, so let me multiply both sides by 3 as well, just to get rid of the fractions. So let's move this equal sign over just a smidge so I can do that. So I'll take the 3 times that. What does that give me on the left-hand side? Well, I need to move this chunk to the left, and I've multiplied by 3. So I've got a delta 2 times 2C2 plus C3, right? This one's going to be what? Minus delta 1 times 2C1 plus C2. Again, I multiplied by the 3, so I got rid of that 3. This here is going to be a 6C1, because I have to multiply by 3. This I can call delta 1, right? So I can call that one 6C1 delta 1, right? This is also delta 1. This is delta 1 squared divided by a delta 1, right? So I get a delta 1, a single delta 1 on top. This 3 on bottom will cancel because I multiplied both sides by 3, right? So we're going to get a 3 times C2 minus C1 delta 1. I really hope I did all my arithmetic right. I'll find out here in a second because the form should come out to be very nice. theoretically. All right. But let's do the coefficient on the C3 because that's really simple. What's the coefficient on the C3? It's just the delta 2, isn't it? All there's left is a delta 2 C3, isn't there? Right? Okay. Now, the other ones we have to do some like terms. I don't think either one's easier than the other, so let's just do the C. Let's do the C1 first. In particular, there's only one delta that's multiplied, one type of delta that's multiplied by the C1, right? Minus 2 delta 1 times the C1, right? Plus a 6 minus a 3. So minus 2 plus 6 is plus 4, minus 3 is just a single delta 1, isn't it? So we'll have a delta 1, C1. Right? Now let's look at the C2s. I've got 2 delta 2s, right? I've got minus 1 delta 1, but I've got a plus 3 delta 1. So I've got 2 delta 1s plus 2 delta 2s. So we get plus 2 delta 1 plus 2 delta 2. Ooh, hey, it's a funky looking 2. Times C2. So that gives me one equation. But notice that that one equation gives me coefficients on C1, on C2, on C3. If I move it up a notch, I get coefficients on C2, C3, C4. If I move it up another notch, I get coefficients on C3, C4, C5, right? All the way until I get to Cn minus 1. Right? Because Cn minus 1 is the last one we have in our list, isn't it? Okay? So, to that end, we get an issue because from a linear algebra perspective, because we've got n minus 1 coefficients we need to solve for. C1 out to C sub n minus 1. But notice that our first equation involves 2 extra coefficients. So, instead of getting n minus 1 equations, we're going to get n minus 3 equations. We're not going to get enough information to solve exactly for all of the C's. Okay? You're going to get, from a linear algebra perspective, you'll get infinitely many solutions. You'll never get no solutions. There's always cubic splines that go through given points. Okay? As long as you don't have 2 points that are sitting on top of each other. Okay? As long as you have n distinct points that are not on a vertical line, and not any 2 of them are on a vertical line, you always get a cubic spline that goes through them. Okay? The problem is that right now, the way we have this set up, we don't have enough information to get an exact solution, and we're going to get infinitely many. So we get to make a choice of how we might want to set this up. Okay? The way we're going to choose to set this up is a couple of things. We're going to do what's referred to as a natural cubic spline, and we'll talk about other types of cubic splines later. The natural cubic spline, it forces an inflection point at the leftmost knot and the rightmost knot. It forces the second derivative to be 0 at those 2 spots. Okay? If we force the second derivative to be 0 at the first left endpoint, then that's going to force C1 to be 0. Okay? So we're gonna force that one. The last one's also, we're going to introduce a new variable. We'll call it Cn, if you will. And it will give us the last one. The last one would also have to be 0. So what we end up with, if I think about how you would write this as a system of equations in a matrix form, your first row of your matrix would be a 1 with a bunch of zeros, because we're going to say something about what C1 has to be. Okay? Right? And then we know that the first equation would have a delta 1, a 2, well, let me move these over a little bit. A 2 delta 1 plus delta 2, and a delta 2, right? We agree with that? Okay. And again, we're going to go all the way over. The rest of these, of course, would be zeros. Yeah, it's 2 delta 2, thank you. I think I said it, but I didn't. Now the next one gets moved over, right? C1, this was C1, C2, C3. The next one will be C2, C3, C4, right? And then everything's going to get moved up. Instead of delta 1, we'll have delta 2. Instead of delta 1 plus delta 2, we'll have delta 2 plus delta 3 and a delta 3, right? So we'll get a 0 here, a delta 2 here, a 2 delta 2 plus delta 3 here, a delta 3 here.
Why is it critical setting of 1?
Because this is the one that we're going to force, I haven't set up the constants on the other side. This is the one we're going to force to be the second derivative to be 0 at the time. We're going to force, yeah, the first constant will be 0 on the right-hand side. Yeah, Haley.
So the 2 delta 2 plus delta 3.
Yeah, it's another 2, yeah. Apparently I can't remember to write the 2 on that one. All right. The next one, what's going to be the first 2 terms? 0, 0, and then we'll have delta 3, 2 delta 3, delta 4, plus 2 delta 4, delta 4, and so on down the line. So we're getting what's referred to as a tridiagonal system. You're probably familiar with the main diagonal of the matrix from upper left to lower right. This is tridiagonal because I get these 3 diagonals that are going down. We'll keep going. You'll keep going with this idea. The last one that you'll get to, on the very, very end, you'll have a delta n minus 2, a 2 delta n minus 2 plus 2 delta n minus 1, and a delta sub n minus 1. And then our last row will be a row of zeros up until the last one will be a 1. So this is, again, to give us enough information to solve the system. So we have this big matrix. We're going to solve for the C1, C2, up to Cn. But again, that last Cn really is going to be a 0, because we're forcing the second derivative to be 0 on the last one. Cn is kind of the last one that we stuck on the end to force it to have an inflection point. And then your constants will be 0 for this one, so that's forcing the C1 to be 0. Then we've got the 3 delta 2, delta 2 over little delta 2 minus delta 1 over little delta 1, and a 3 delta 3 over little delta 3 minus delta 2 over little delta 2, 3 delta n over little delta n minus, or n minus 1, sorry, minus delta n minus 2 over little delta n minus 2, and then 0 on the end. Oh, hey, that was fun. All I'm doing on the right-hand side there is just rewriting these coefficients, these constants, increasing the index by 1 each time. Okay. This gives us a square system that we can solve exactly. Now again, we're doing what's referred to as a natural cubic spline. meaning that we're forcing an inflection point at the first and last knot. That's not the only way to do it. Okay? There's a couple of other possibilities that you could use. You could force what the second derivative has to be, force what the cubic curvature is. Maybe you want it to be an actual curvature and not just an inflection point. You can force it to be a quadratic on the first and last knot. There's other ways that we can approach how to get this extra information that we need in order to be able to solve the system.
So
Okay.
last time how did that come from the left? Like the last mistake there.
Yeah, we come from the left or from the right. Because all of these are just polynomials, so we can take the derivative and then look at a limit from the left or the right. If we would like to. Yeah, they're all polynomials. Yeah, so we're just extending it. Yeah, that's all we're doing. Yep, you're right. Okay, so we don't have a lot of time left, so what I want to do is show you how we can make this tri-diagonal system thing, this little trick on Excel that I Googled. It's amazing what you find on Google. So let me show you how that works. So let's go into Excel, not with the Boeing stock, because I'm going to do that later. All right, so let's say that we had some x's and y's that we wanted to interpolate with cubic splines. So I'm just going to put some headings in here. Let's say that I make up the point 1, 4, 2, 7, 4, 4, 7, 3, 9, 8. Doesn't matter. I'm just making up numbers. Okay. Okay, so one of the things that we need in order to be able to set up the system are your little delta sub I and your capital delta sub I, right? Right? Okay, so to that end, I'm gonna put it down a row, only because remember we're gonna add that first row with a 1 and a bunch of zeros, and the bottom row with a 0 and a bunch of 1s. So I'm gonna put these down here, down a row. So this one will just be equal to A3 minus A2. And the next one, of course, will just be B3 minus B2, so I can just copy it over and copy it down. So those are our deltas, little deltas and big deltas. Oh, again, I literally just typed in this cell. I just typed in equals A3 minus A2, copied it over, and then copied everything down. Because that's all I'm doing is subtracting consecutive cells in both of them, right? All right, so then remember that your entries in your matrix are what? Well, they're the delta 1, the 2 delta 1 plus delta 2, the delta 2, right? And then the delta 2, 2 delta 2 plus delta 3, and so on down the line, right? Okay? So we can get those pretty easily because I've got the little deltas here, right? So I can set this up in a rectangle pretty quickly, right? Pretty easy. We can set it up in a rectangle. I need to do equals delta 1 is in C3. I can type the number 3. All right? That was delta 1. Right? We agree? And then this one is 2 times C3 plus 2 times C4. Right? 2 delta 1 plus delta 2, 2 delta 2. And then equals C4. That's the delta 2. And then I just literally need to copy this down. Just need to take that and copy it down because it'll be in the right cells. All right? Do you agree with that? Yes.
How did you get that column name? Like what you call
This one was just equals the next delta down. Because remember it goes delta 1, 2 delta 1 plus delta 2, and then delta 2. And delta 2 is the next one down. Yes, we're going to want to shift those. This one. Actually, I don't need this last row because this is not the last one. I don't need this last one. I just need the 3. Because remember, our first C1 that we use is going to be 0. And the last C1, the last CN is a dummy one. Right? It's just a forcing of the last inflection point to be, not to be an inflection point. I just need those 3. Because we have C1 for free. C1 is going to be 0. So I just need C2, C3, and C4. So I only need those 3 rows. But you're right, we want to shift those. That's not the way we want a tri-diagonal system, right? That is not tri-diagonal. So here's a little trick that I learned on Google. This is a fun little trick. Would not have thought of this myself. Seriously, would not have thought of this myself. All right. In Excel, there is a command called if-error, which means that you can use this if you're doing something in here and say you came across a division by 0 error, you could tell Excel how to handle the division by 0 error by itself. If there's an error, then make it 0 instead, which is exactly what we're going to do. Okay? So here's how we're going to run this. We've just made an array. So we're going to use the index command here. All right? This is the array that we want to index. Okay? I want to be able to pick out these individual things by column. So here's what we're going to do with this. So the first thing I'm going to do is I'm going to select the array. So I just selected the array. We want absolute cell reference on this array. I don't want it to change as I copy this thing. Okay? Now I want it to, basically what we're going to do is we're going to pick out a column index where we want it and have it print the number that's in that column for that row. Okay? Now, we only want it to do that if there's not an error, because we can get an index that's too small or an index that's too big, and that's when we're going to put the zeros in. To figure out where we want that, this is kind of weird, but I'm going to put 2 commas in there. We're not going to. The reason why I'm doing that is I'm not specifying the row. I'm going to specify the column, because again, I want to go across the column. So here's how we do it. There's a command called columns. Now this part is a little weird. I want to start counting columns with the column that I'm typing in, because this is where I'm going to start the matrix to form. I want that to be an absolute cell reference. And then I want to stop. I want to start my matrix here. So that's why I made this fixed, right? This one I want to be relative cell reference because I'm going to copy and paste. And I want that one to change. Okay? So what that's going to do is it's going to count how many columns have been built so far. And then we're going to do the same thing with the rows. So I'm going to close this off and do the same thing with the rows. Like I said, this is a lot more clever than I would have ever come up with. Same idea. Start at J3, do an absolute cell reference. End at J3 because that's the current cell that we're in.
Or minusing the rows?
Yes, subtracting the rows. Basically what we're doing with the columns minus the rows is we're trying to create an error. If we get too many more rows than columns, we're just going to automatically put a 0 in, so that we can shift everything. As we're going down the rows, the number of rows will outweigh the number of columns until we get to the diagonal, and then we'll start putting them in. And then we'll get outside of the range of the array that we've built, and then we'll put zeros on the end. That's what this is going to do. All right? To make sure that we start indexing with 1, we're going to put a +1 on here. Okay? So again, what this is going to do, this part here is going to shift everything down to the right for what's in this array. Otherwise, we might get errors. In the case that we get an error, we want the errors, The errors are where we want to put the zeros in for the tri-diagonal matrix. So if we get an error, we're going to print a 0. Otherwise, it's going to just take the element out of the array where we want it. Okay. I know, it's a goofy looking command. Okay. All right, so hit enter. Notice the 1 pops up. We're going to end up with what size of matrix here? Well, again, we're looking for, we know C1, we're looking for C2, C3, C4, and we have a dummy of C5. So I need to copy this over to make a 5 columns, and then just down. And you can see it shifted things over. Now I made the tri-diagonal matrix. Okay. It was a nifty little function that somebody came up with. All right. Then on top, remember I still need the dummies, right? This one's forcing the first C1 to be 0, and then the last one forces the dummy Cn, in this case C5, to be 0, right? And then we need the constants. The first constant is 0. The last constant is 0. And then these constants are 3 times delta 2 minus, or delta 2, which is in D4, right? Oops. Must have thought I hit enter. D4 divided by C4, that was delta 2, capital delta 2 over little delta 2, and then minus D3 divided by C3, right? We agree with that? And then we just need to copy that down. Okay. So now we've set up our if you're doing the language of linear algebra, we've set up an augmented matrix, right? 5 equations, 5 unknowns, augmented a constant column, right? So to solve this system, I want to do row reduction. Well, you can do this in Excel, and if somebody asked about extra credit possibilities without doing computer programming, figure out how to do row reduction in Excel. There you go. There's an extra credit possibility if you'd like to do that. Okay? Okay? And I don't mean using the equation solver that's built into Excel. There's a solver pack that you can do. Don't do that. I want you to actually come up with a method for doing it in Excel if you want extra credit. I'm going to use Geogebra because I don't have to do Excel that way. Plus, Geogebra, we can graph things. So go over to Geogebra.
Is that just like the classic one to download?
Yeah, you can do the classic one. I'd rather do the other one though. Go over to Geogebra here sometime today. View. I want to open a spreadsheet. And I'm going to expand it a bit here. What's nice is that now I can just copy, go back over to Excel and copy those numbers. I can paste it into Geogebra. By the way, I am recording this today, so if you want to go on YouTube later and look at it, you can. Okay. And paste, ta-da, goes into Geogebra spreadsheet. Okay. Now, why is that helpful? Well, Geogebra is a computer algebra system. I highlight those cells, I right-click, I create a matrix. Now I have a matrix that I can refer to over here. Okay. I'm not going to do it today, but I'm also going to use Geogebra to finish off these splines and show you how you can graph them. And you can actually see it. Which is what we probably see I had that Boeing file opened up earlier. We're going to do cubic splines on a Boeing stock price. That'll be next time. All right, but now if I want to solve this system, down at the end, you can't see it because of this. The input bar is at the bottom. It's blocked by the pause button on the recording. Okay. The command is reduced row echelon form. You can see it popped up here. Okay. If I just hit tab, no, not tab. If I just click on it, the matrix, it gives me a name for the matrix M1. There's my matrix. Yep. So now I've got the C's. Remember again, once we have the C's, we can get the B's and the D's, and then I can form the cubics, right? Here's what else is nice. And this is the last thing I'm going to do, and then we'll finish this up next time. I can take this matrix, click on it, and drag it over, and it'll plop the entries down to the spreadsheet for me. And now I can use those C's and do the computations from theirs. From there, not from theirs. Okay. So next time what we'll do is we'll finish this cubic spline example up and show what it looks like with a graph, and then we'll do a bigger example. All right? Enjoy. I get to go have my teeth cleaned with.
I had one last semester.
Oh, yeah. Okay. It's a root canal on the same tooth. Oops, sorry.
Okay, so we're gonna be gone again Thursday.
Okay.
We're traveling to Greenville.
Okay.
Here's my